Hello all, it's Andrew Engineer, alright. So has been long. Today we are going to talk about load distribution, alright. So in the last one of our video, we spoke on how to make the pre-dimensioning of a column, okay, reinforced concrete column. So today we are going to show you I'm going to explain you how to make the load distribution, or yes, the load distribution on the floor, and at the end of the video you'll be able to evaluate the load of the inference area that is being applied or being carried by the column, a reinforced concrete column, such a way that you can have the exact value of the load that will be used for the design of that reinforced concrete, so that you'll be able to provide a section of the steel needed for the reinforcement. All right, so thank you very much. Let's explain. Here we have a section of our building which is a G+2. All right, let me call it name it G. All right, so this is the ground floor, or this is the ground floor, that is the G+1. This is the first floor, second floor. Okay, so here you can easily see the arrow in black here are to represent the load repartition on the structure. Okay, so this beam, for example, is starting right up to the roof going down. Okay, it's starting right up to the roof going down. What happens is that the load sent by the roof truss, okay, the roof truss will be received by the chaining beam here at the roof, the chaining at the roof level here, which will share that load into two, send it to this intersection where there is a column. Half will be sent the other way at this other intersection where there is a column. Such the column will take down the load to the next level down. Okay, and this floor here will also share. This is a beam carrying the slab, okay, which will be sending half of its load this way and the other half on this column or on this joint, which will be received by the column to the next level, so doing till it will reach the dwarf pillar, okay, and be received by the footing, which will by its own send it to the ground. Okay, so that's how load is being transferred, or load is being transferred from the rooftop to the ground. Okay, that's why in nowadays, or mostly, you heard they will say the structure is more lighter as we going up, because normally the section of the column, for example, at the dwarf pillar level here will be different, or at the ground floor here, or here the ground level here will be different from the section, or will be bigger from the section at the first floor, which will also be bigger from the section at the second floor, which will be lighter than the section at the first floor. Okay, so as we are going up, normally the section of our structural element are supposed to be decreasing. Okay, that's to optimize the cost of the building, and you can understand why this structural element, which is the column here, is bigger. Is simply because this column of the ground floor is carrying the two other floors up. Okay, and this one is carrying the other one floor up, so it's normal that you should have a bigger section to be able to carry more load. Okay, so here you have a 2D representation of the floor plan, okay, of one level, considering the spatial of organization has not changed. All right, so this is the spatial organization. How do we get the load which is being applied on this column for the design of the reinforced concrete column? If we consider, for example, here the case of the axis A and 1, the intersection of A and 1, you have the column A1, which is at the angle here. The inference area will be divided at the center of this beam. Okay, first of all, before even dividing it, you have to check whether it's a one-way slab or a two-way slab. And how do you check whether it's a one-way slab or a two-way slab? Because you have to know it to know the load repartition on your beam or on the structural element of your structure. So you make the short span, okay, short span divided by the long span. You should check for a one-way slab, the value should be less than 0.5. For a two-way slab, it should be equal or greater than 0.5. 0.5. Okay, so to have a one-way slab, you should make sure that the ratio in between the short span and the long span is less than 0.5. If we take this case, we have a span of 3 meters here, divided a short span of 2 meters. So if we take this slab, this portion of the slab or this room, we divide 2 by 3, it will give us approximately 0.67, which is greater than 0.5. So normally this room is supposed to be carrying in two way. Okay, if you are to represent the way of the direction of repartition of load on that slab, it will be in 2 way. So it's a 2-way slab. But since for the sake of this exercise, we have choose to work with a ribbit slab. Okay, we are working with a ribbit slab, and knowing the context, the geographic context of where we are actually, which is Cameroon. Okay, in Cameroon, usually most often when we are working with a ribbit slab, we are considering a one-way slab. So we simply orientate it in the load in the direction of the shorter span. So we will just divide this floor into 2 according to the short span. Okay, and the load will be distributed the way you can in the direction of this arrow. Okay, same way down here you can be represent them this way. Okay, so like this you can quickly see how load will be distributed, and you can see that these beams are working more than this other external beam here. Okay, because it's a one-way slab and this is the shortest span, so the load is being transferred is being distributed along the short span to reduce the moment. Okay, to reduce the deflection. Okay, so I have made a video where I explain how and why the orientation of the column or the beam in a 2D drawing is being important. You can check on the channel there. So this is it. Once you have the repartition of load, now you can find the inference area where on the column A1, okay, at the intersection of the axis 1 and the axis A. So if you are to cut it, this is the inference area of this column A1. This is it that I have represented here. The length will become the half of this span of 2 meters, which is the 1 meter, and the length will be the width instead, and the length will be half of this span of 3 meters, which is 1.5. This is how you present it. Okay, and has other factor that I did not mention will be considered to know which is the most loaded column here. The permanent load has the main factor. Okay, yes, we'll use the permanent load as a main factor to evaluate which column have the most which column is the most bearing, or the column that is carrying the biggest load. Okay, yes, so this is the inference area of column A1. If we look at column B2, okay, this intersection between the axis 2 and axis B, you have column B2. You can easily section it this way. Okay, you can see that this will be the influence area of column B2. So let me try to put a blue marker there, though it's no more blue. This will be the influence area of this our column B2. Okay, so you can easily see that the influence area of column B2, which is located at the center of our structure, is bigger than the influence area of column A1. And even if you are to take the influence area of column A2, you will still be B2 having the biggest influence area. So this column is carrying the more according to the permanent load. Okay, I said the main factor that we'll consider to evaluate, because the live load might also have a certain influence depending on the purpose of the building. Okay, so but here we are considering as main factor or main criteria the permanent load. So this is our biggest influence area, and we use it to analyze, so that to evaluate the load that is being received and that is being used for the design of this column B2. Okay, to do that is very simple. We'll call it as I've named it already, the surface area S1, S2, S3, S4. So we evaluate the load. I'll call it LS1, which is the load of this area, considering that we have a ribbit slab. Okay, so we'll be having the length multiply, we'll just multiply the self weight, the self permanent weight of the ribbit slab, which is 2.85. Okay, which is 2.85. Okay, multiply by what? Multiply by, let me change the marker, which will be multiplied by the width, which is half of this, which is half, S1 is here up here. Okay, the width is half of this span of 2 meters, so it's 1 meter, so multiply by 1 meter. Okay, and then we will also multiply by the length to have the inference, this small inference area. The length is half of the span of 3 meters, so it's 1.5. Okay, so we'll have 1.5. At the end of the day, if we punch it, we'll have 2.85 multiply, which is given 2.85. This permanent load is given in your Eurocode 0. Okay, or you can get it in NFP, the norm française NFP 01/04. Okay, you can get the permanent load, the live load, depending on the purpose of the building there in those code. Okay, whether it's Eurocode, Bael, or yes. So times 1 times 1.5, so we'll have 4.275. So we can round it up to 4.228 kilonewton. And remember, as is the load that is going directly to the column, we'll be giving the load directly in kilonewton. Is it okay? So if we look at the load given by the surface area 2, okay, sorry, we'll be having 2.8, the self weight of the ribbit slab. Okay, multiply by the width, which is area 2 is down here, so it's half of the span of 1.5, which is 0.75. Okay, multiply by the length, which is still the half of the span of 3 meters, which is 1.5. So at the end of the day, we'll be having 2.85 times 0.75. Okay, 0.75 times 1.5, that will give us 3.2 kilonewton. Okay, that's 3.2 kilonewton for the load carried by given by a surface area 2. Surface area 3 will give us a load of 2.8. Remember, we are calculating according to the self weight of the ribbit slab. Okay, times the length here, area 2 is this area here, so the length is half of this span of 4 meters, which is 2 meters, times the height here, area 2, which is half of 2 meters, which is 1 meter. Okay, so it will be equal to, we punch it, 2.85 times 2 will be equal to 5.7 kilonewton. Okay, so we just obtain LS3. We'll also look for the load of surface area 4, which is equal to 2.85 also, times what? Times the length. S4 is down here, so the length is half of this 4 meter, the length of the span, and then the width is actually half of 1.5 meter, which is 0.75, which will give us what? Oh la la, sorry, 2.85 times 2 times 0.75, it will give us 4.27. Okay, 4.27. So we can round it up, sorry, one minute. We can round it up to 2.8 kilonewton. Okay, it will be 4.28 kilonewton. Now you will realize that we just calculated the self weight of the various small surface area which constitute the inference area of column B2. Okay, now we also have to consider the self weight of the beam carrying those load to send them, because remember, it's the beam that are sending those load to what? To the column. Okay, so we have to calculate the self weight of each of these half beam. Okay, for beam 1, beam 2, beam 3, beam 4. Okay, so the self weight of the self-weight of beam 1, for example, self-weight beam 1 will be equal to what? Beam 1, we already know the cross section 20 by 40, okay? The length of beam 1 is beam 1 up here, so the length is 1 meter, okay? Sorry, oh la la. So 1 meter times what? Times, let me just try to change the marker. 1 meter times what? We'll be having 1 meter times which is the length of the beam, times its cross section 0.2 times 0.4 times the self-weight of reinforced concrete, which is 25 kilonewton per meter cube. Okay, we'll make the numerical application. 0.2 times 0.4, because we converted it in meter, it was in centimeter, times 25. Okay, it will give us 0.2 times 0.4 times 25 is giving us, okay, I'm multiplying instead by 15. Let me say 0.2 times 0.4 0.4 times 25 is giving us, what is this? So 0.2 times 0.4 times 25 is giving us 2 kilonewton. Okay, 2 kilonewton, the self-weight of beam 1. So self-weight of beam 2 will give us what? Beam 2, this beam 2 down here, so the length of beam 2 is 0.75. okay, half of the span of 1.5 meter times the same cross section 0.2 0.4, okay, times 25, which is the self-weight of reinforced concrete, is gonna give us, since the only thing that changing between the two is the length, which is 0.5, it give us I think is 1.5 kilonewton. Okay, that's mental calculation for SB3. Okay, for SB3 now, SB3, this is our beam 3. The length of beam 3 is equal to what? Beam 3 is here. This is our beam 3. The length is 1.5. Okay, so 1.5 times the same cross section, nothing has changed. Okay, times 25 is gonna give us what? 1.5 will give us 3 kilonewton. That's mental calculation again. Okay, so now SB4, okay, for beam 4 is gonna give us, we have 2 meter. I'm sure beam 4 is this one, half of this 4 meter span times the same cross section. Okay, 0.4 times 0.2 times 25 is gonna give us what? Is gonna give us 4 kilonewton. Okay, so we have the self weight of everything. Now we can just sum it up, all this, to represent it as the weight that is being received by what? By our reinforced concrete column. Okay, plus 4 plus 3 kilonewton plus 4.28 plus, I'm summing even with the portion of the small surface area, ls1 ls2. I will sum everything to represent the load received by that beam, that column b2. Okay, plus 5.7 plus 3.2 plus 4.28. You need to be really focused to avoid making mistake. Okay, it's giving 26.46. okay, 26.46. Let me just write it down and make sure and punch it again once more. It's 4.28. This first one was 4.28. okay, so if you are to say the weight received by the load received by column b2, will be equal to what? To 26.46 kilonewton. That's the load received by the column. But let me just punch it once more. So the first one that we deleted was 4.28, okay, plus what? Plus 3.2 plus 5.7 plus 4.28 plus 2 kilonewton plus 1.5 kilonewton plus 3 kilonewton plus 4 kilonewton, 27. Okay, That's the value. 27.96 instead is 27.9x, 27.996. Okay, I surely missed out something in the first calculation. So this is the load received by our column, okay, B2. Now we have to consider for the design. I told you at the beginning of the exercise that we have to find the load used for the design of that column, okay. So we have to consider also the self weight of the concrete, because remember, it's simple to see it. You cannot do it without the self weight, simply because just take the real life situation where you are very sick. If you are very sick, you are so weak such a way that even to carry a container like this, a 1.5 liter container, you don't have the power, so you cannot even carry your self weight. That's why in the design you have to consider your self weight, okay, because you are also carrying your self weight before being able to carry in this container of water. I don't know if that example looks clear for you, okay. That's why we need to consider the self weight of the reinforced concrete and add it to this load received by the reinforced concrete, which is the load that is being carried by the reinforced concrete, okay. So to calculate the self weight of the reinforced concrete column B2, okay, will be equal to what? We have the cross section 0.2 times 0.2. We have the height of the floor to floor here, which is 3 meter, okay, times 3 meter times the weight of the reinforced concrete, which is 25 kilonewton. We just punch it quickly. We have 0.2 times 0.2 times 3 times 25 kilonewton per meter cube. That's giving us 3 kilonewton, okay, 3 kilonewton. So to have the final load to be designed, to be used for the design, okay, they say one step to consider. We'll have the final load final LF, okay, is equal to 27, which we can round up to 28, okay. 28 kilonewton. Is always better to majorate it. Is it okay? Yeah, 28 plus 3 kilonewton, which is gonna give us 31 kilonewton. So normally, if you are to design, this should be the load that we are to consider, but there's still one detail to consider: the fact that we have to consider the surround of that column to see whether that column is near to an external column or not. And if yes, if it's near to an external column, how many external column is it near to? Because if it's near to one external column, we measure the load, this load, by 10%, okay. We add 10% of this load on it, okay. If it's measured by more than one external column, like in our case here, because we can see that column B2 is close to this external column, which is B3, also this one, which is C2, also this one, which is B1, and also this one, which is A2, okay. So it's close to 4 external column. So according to BIEL, according to the norm, okay, because we are designing according to a norm, okay, according to BIEL, we have to measure this load by 15%, because more close to more than one external column is already measuring by 15%, okay. So the load, the final load for the design, that's why I'm adding D, because this is the one that we'll use for the design, will be 31 kilonewton plus 31 times 0.15, okay, which is giving us what? Which is giving us 31 plus 31 times 0.15 is giving 4.65. So we can say that it will be 31 plus 4.65, okay, which is finally equal to 35.65 kilonewton. And to measure it, because we are always analyzing in the worst case scenario, so better in the phase of designing or conception, add your load and trace your structure somehow, okay. We'll just say that LF is equal to LFD for the design is equal to 36 kilonewton, okay. It's better to just measure it. Remember, even in using the norm, is not for nothing that we have the safety factor like 1.5 for the live load and 1.35 to the permanent load, according to BIEL, okay, or to Eurocode. They have the same safety factor, okay, though they might change at some level. So always try to measure it, because depending on the purpose of the building, you are not sure, for our context, African, for example, you are not sure that designing your structure to be a residential building will be used till the end by to be a residential building. At the end, you might hear the landlord or the project owner change the building to be a snack bar, which already have different livelihood. Okay, so that's also the importance of trying to measure, because as an individual, you should always be able to justify your result. Thank you so much. It was Andrew Engineer.